Okay, customize data and feature references. Their desired degrees of freedom noted following each data and feature reference, if necessary to take exception to default constraints. Lowercase letters for notations, and coordinate axes labeled with uppercase letters in the model or drawing. Okay, coordinate system display and labeling. Its associated coordinate system is shown and labeled if one or more customized datum reference frame is created, and different based on the model versus or orthographic view. So over on the left, we've got the coordinate systems called out with letters for the datums and arrows pointing to the direction. And in the model, you have your your full 3-axis coordinate system trihedron that shows where those locations are and the notation next to them. Okay, customizing datum feature references. You're going to specify degrees of freedom to be constrained by the datum feature reference. Notation indicate constraint degrees of freedom. Can only note those possible for datum features. And shown with lowercase letters and brackets following datum letter and any applicable modifier. As many datum features as needed are referenced until all desired degrees of freedom are constrained. Okay, datum features of size at RMB, MMB, and LMB. So material boundary modifiers applied to the datum feature references have significant effect on the tolerance requirements. Datum feature surfaces at RMB, MMB, and LMB. Application of material boundary modifiers on surfaces may be done only when material boundaries created for the surface, though application of profile tolerance, through the application of profile tolerance. Offset datum features to constrain rotation. Datum feature offset from a higher precedence datum axis sometimes utilized to constrain rotation. Simulation different based on RMB, MMB, and LMB. So here we have a part where we're trying to control the rotation. And we have a tolerance of 100, or a distance of 150,000, but you have a profile tolerance of 0.002, which gives it some freedom for movement. Okay, simulated offset datum features at RMB, MMB, and LMB. So here we have some examples. On the first one, maximum material condition and maximum material boundary are applied on datums A and B. Sorry, I misspoke. Maximum material boundary specified on datum A and B, and regardless of feature size for the actual component, feature is assumed. So the simulator is fixed at maximum material boundary, and the simulator is fixed at MMB. So when it's at maximum material boundary, then you don't have any more rotation than the difference between MMB and LMB. An example on the bottom, datum B is basic. A simulation of offset datum features at basic. Secondary or tertiary datum feature noted to be indicate datum feature simulator applies at basic location and orientation. Basic shown following the datum feature letter. BSC shown following the datum feature letter. Basic dimension value in brackets shown following the diameter feature letter. And a drawing note explains simulator is not to be fixed at the basic location. And the datum feature simulator fixed in location and orientation to a higher precedence datum features. Restrained datum features. There may be the need to indicate allowable restraining force in a note. Parts subjected to distortion or deflection that impact establishing repeatable datum reference frame. Examples are automotive body panels and aircraft structural parts. Use caution to avoid any potential negative effects of excessive force. And free state requirements typically needed when restrained part requirements are specified. Dimensions related to a datum reference feature. Some parts of industry control feature size and orientation relative to a datum feature references. Established by a note in the product definition, and relate dimensions with plus and minus tolerances to a datum reference frame only if design requirements dictate it necessary. You can usually be avoided by using profile tolerances. Putting this in practice is a whole nother thing. Once you start using profile tolerances, sometimes it's difficult to measure on the shop floor. So I'm not sure I agree with this in practice. Datum features on molded and cast and forged parts. Okay, they have what's called a parting line. The parting line is where one piece of tooling ends and the other one starts, and it typically leaves a witness line where the mold or the forging dies separate. And it's often used as a reference. The parting line is the line on which two segments of a mold tool separate. Mismatch between tool segments can result in a step in the part surface at the parting line. And place the datum targets on one side of the parting line, so you don't want them on both mold halves. Okay, draft is an angled wall, and it helps the material come out of the mold. And it's an adequate angle designed on the part surfaces to permit removal of the part, pattern, or wax from a mold or die. And it's best to select raw part datum features that remain unchanged in final part if possible. So if you're machining that draft off, you don't want to use that as the datum. Here's an example of a raw part datum features. This would be a casting. So it looks like they have datum A. It's 3 targets that are on the bottom wall of the inside of this casting. And then we have datums B1 and 2, because you only need 2 to do a secondary datum. And they're on the back wall. And then datum C is the right side wall of this cast part. Now remember, the tertiary only requires 1 point. So if you were to set this up or to inspect it, you would need to set up some sort of fixturing or tooling that would contact those parts on those irregular surfaces. And this appears to me to be a casting. If you see the phantom lines, top and bottom of the part, and the hidden lines for the holes. I believe the phantom lines represent the material as it comes out of the mold, and then the solid lines are after that material's been machined off and the holes have been established. Okay, here's datum features on additive manufacturing parts. I hadn't really thought too much about additive manufacturing, but I think it's pretty darn hard to keep track of datums. So if you were to grow something and it has a support structure, you might think about building in features that are going to become your datums. And that way, if you have to do other work in an assembly, perhaps you're doing post-op machining on that additive manufacturing part, casting, whatever, you've got your look documented. So in this case, they got datum targets A1, 2, and 3, which create a simulated datum, and you would have to have measurements to where those contact points are on this curved surface. Okay, so the datum features are single part with all required features can be printed. Identification of datum features and application of the tolerance on important internal features present challenges. And not all features are continuous or accessible. And theoretical supplemental geometry, not approved by any standards yet. So there is a standard on additive manufacturing, but it's not in the geometric dimensioning tolerancing standard for on how to use datum targets. Okay, in summary, this unit focused on advanced applications of datum references, including how a datum reference frame can be simulated using 3 mutually perpendicular surfaces. You learned how to apply material boundary modifiers to datum feature references, and understand their impact on manufacturing and inspection. Additionally, you explored how datum features constrain specific degrees of freedom within a datum reference frame. This unit also covered the use of a movable datum target symbol and the application of the translation symbol to datum feature references. By mastering these advanced concepts, you are able to apply GD&T principles more effectively in complex engineering designs. Okay, in conclusion, by the end of this lesson, you were able to explain how a datum reference frame may be simulated when 3 mutually perpendicular surfaces are identified and referenced as datum features. Use material boundary modifiers on datum feature references and explain the significance of the modifiers. And identify the degrees of freedom constrained by each reference datum feature in a datum reference frame. And explain the requirements of a movable datum target symbol, and explain the requirements of a translation symbol applied on a datum feature reference. Thanks for joining me for this lesson. This concludes Unit 7, which ends at the end of Chapter 6 in our textbook. All right, catch you on the next one.